right, welcome everyone, and thank you so much for joining us for the new Vistas in Astronomy lecture series. This is our 51st year of the lecture series, which started with less than 30 chairs in the old Amato Schoolhouse in Amato, Arizona. For those of you who are joining us from far away and do not know where Amato, Arizona is, it's about 40 minutes north of the Mexican border and about an hour and 20 minutes southeast of Tucson, Arizona. We're really happy that you're here with us today because we're doing something really interesting with our series this year. This year, because we're all virtual, we're able to welcome speakers from throughout the Center for Astrophysics, Harvard and Smithsonian. And today we're welcoming someone from quite far away, across an ocean, in fact, or I guess halfway through an ocean. I'm Amy Oliver. I'm the Visitor and Science Center Manager from the Fred Lawrence Whipple Observatory at the Center for Astrophysics, Harvard and Smithsonian. And I'm going to turn it over now to one of our education lead volunteers, Stephen Brown, who's going to introduce our speaker for you and get things started. Stephen, go ahead.
Hi, welcome everybody. Glad you could join us. Today we have with us Dr. Simon Radford, who is the director of the Hawaii operations for the Submillimeter array on Mauna Kea. Prior to joining the Smithsonian Astrophysical Observatory, he was a member of the professional staff at the California Institute of Technology, where he was the technical manager of the Caltech Submillimeter Observatory. Previously, he was a staff astronomer at the National Radio Astronomy Observatory in Tucson, Arizona, and at the Institut de Radio Astronomie Millimétrique in Grenoble, France. He received his BS in engineering physics from Cornell University and his MS and PhD in astronomy at the University of Washington. His research has included observations of the cosmic background radiation, spectroscopy of molecular gas in distant starburst galaxies, characterization of atmospheric conditions at submillimeter observing sites, and development of telescopes and instrumentation. Dr. Radford, welcome and take it over.
Thank you, Stephen. And welcome everyone. I'm sorry, okay. Welcome everyone. Thank you, Stephen, for the introduction and Amy for introducing the series. I hope you hear me say something if you don't hear me. And I'd like to tell you something today about the submillimeter array. I hope I will explain both of those words and tell you a little bit about what we do with this telescope. This picture, which I'm starting with, is not quite what the array looks like this morning. The sun is just rising here, but this shows you a sunrise view of the submillimeter array. It's one telescope that's composed of 8 antennas, and these are located on the top of Mauna Kea here on the island of Hawaii. What you see in this picture are the 8 antennas of the array, and behind that you see the shadow of Mauna Kea at sunrise when I took this picture a couple of years ago. That's the shadow off to the right. There is also another mountain in the near. That's the mountain of Hualai, which is another of the volcanoes on the island of Hawaii. Okay, so let me start. Oops, hang on. There we go. Astronomers look at light. We have a whole profession that is devoted to studying all of the light that we can detect from the universe. Light is wonderful. It's comes in a wide range of colors of wavelengths, all the way from very long wavelength radio waves up to very, very short wavelength gamma rays. The physics of light itself is the same for all of these variations, but of course, it's the interactions of light with matter that differ from the long wavelength to the short wavelength. At the very long wavelength, radio waves are generated or detected through the bulk motion of electrons largely. When you get to visible or ultraviolet radiation, that's largely generated through electronic transitions in atoms. Electrons in atoms are moving between bound states in atoms. And then gamma rays are generated through nuclear transitions between nuclear states or through nuclear decay. So the different wavelengths of light interact differently with matter, and that's why we astronomers study different wavelengths to understand different aspects of matter in the universe. So this chart shows a spectrum, a very broadband spectrum. The wavelength running from very long on the left to very short on the right. The visible light that we see is in the middle. It has the familiar colors. And the wavelength of visible light is about one half of a micrometer. And the submillimeter array observes light with a wavelength of just less than a millimeter. So about 1,000 times larger than the wavelength of visible light that we can see with our eyes. Another thing on this graph to point out is that the temperature of an object, if you heat up an object, the temperature at it will radiate light. I'm sure you've all seen a hot piece of metal, perhaps a piece of iron in a blacksmith shop that glows cherry red, and then as it gets hotter, it glows orange, and finally it glows more yellow white. That color change depends on the temperature. So by looking at the color of light, looking at the wavelength of light, we can tell something about the temperature of the object we're looking at. So the submillimeter radiation that we observe with the submillimeter array has a wavelength of just less than a millimeter, and typically we can look at cold objects which are less than 100 Kelvin, cold objects in the universe. Why is submillimeter radiation interesting? If we look at the total amount of light in the universe, this spectrum shows the intensity of light against wavelength. There's three large areas of the spectrum where we find light in the universe. The most energy, the most dense radiation is the cosmic background radiation, microwave background radiation, this gray bump over on the left. But then there are two smaller bumps. The cosmic background radiation is primordial. It comes to us as a relic of the very, very early universe and has been only very lightly altered since it was emitted in the very early universe. So it is a valuable probe of early times in the universe. The other two bumps, which I've labeled in blue, the optical and near infrared, and in red, the far infrared and submillimeter, represent starlight and reprocessed starlight. Stars radiate in the optical and near infrared, but often their radiation is then absorbed by interstellar matter and then re-radiated at longer wavelengths in the far infrared and submillimeter. And those two, the energy density in those two bumps in the spectrum is about the same. So there's an equal amount of information in the far infrared and submillimeter as there is in the optical and the near infrared for studying star formation in the universe. Okay. The light does not penetrate our atmosphere equally at all wavelengths, which is generally a good thing for us. It's only at certain windows that we can see out into the universe. The visible light is, of course, one of those windows, and that's part of the reason it is visible, of course. We can look out on a dark night and see the stars. We can look out on a clear day and see the sun. We can see through the atmosphere a long way in our daily life. But short of that, in the ultraviolet and even shorter wavelengths, those wavelengths do not penetrate the atmosphere. They're absorbed by ozone and other molecules in the atmosphere. At longer wavelengths, the near infrared, there are some windows, but the atmosphere becomes increasingly opaque to the far infrared because of water vapor in the atmosphere. And then in the radio, the atmosphere becomes transparent again. The submillimeter is on the long wavelength end of the water vapor absorption in the far infrared, but it is only partially, the atmosphere is only partially transparent in the submillimeter, and it really depends on the amount of water vapor, which means that for observing in the submillimeter, we need to put telescopes at very high, very dry places, such as the top of Mauna Kea. Here is a picture of some of the SMA antennas on Mauna Kea. The altitude of Mauna Kea is almost 14,000 feet, and that puts the summit above perhaps 90% of the water vapor in the atmosphere, and allows us to look out at submillimeter wavelengths to observe celestial objects in a way that we could not do at a sea level site. In the background, you can see the island of Maui, Haleakala, surrounded by some clouds. The clouds are all below the summit in this picture. And these are the conditions that we like to see on Mauna Kea when there is a temperature inversion below the summit of Mauna Kea that traps the water vapor. After all, Hawaii is in the middle of an ocean, and there's plenty of water out there, but the water vapor, the marine water vapor, is trapped by a temperature, often trapped by a temperature inversion, and so it does not rise to the level of the summit, and the conditions on the summit can be very dry. And you will notice there is an absence of vegetation in this picture, which is indicative of very dry conditions. At this point, I should say that the submillimeter array is operated by the Smithsonian Astrophysical Observatory in partnership with the Academia Sinica Institute of Astronomy and Astrophysics in Taipei, and under agreement with the University of Hawaii. And we are grateful to the people of Hawaii, to the state of Hawaii and the University of Hawaii for supporting astronomy on Mauna Kea and allowing us to operate telescopes there. The SMA, as I said, is one telescope. It has 8 antennas though, and this is a close-up of one of these antennas. Each antenna is 6 meters in diameter, this primary surface, about 20 feet across. It's made of 72 aluminum panels, and you can, if you look carefully, you can see the rectangular rectangular panels that make up the primary surface. And these aluminum panels are mounted on a carbon fiber and invar truss that holds them in place. The overall surface accuracy of this primary mirror is about 12 micrometers. And since we observe at wavelengths of just less than a millimeter, this is something like 1/8 of a wavelength surface accuracy, which is quite good for these wavelengths. We have 8 of these antennas, and we have on site a hangar where they were assembled, and we conduct maintenance. We have to do regular maintenance on them in a hangar. So now I'll explain a little about how 8 antennas can work as one telescope. In a conventional telescope, the light is collected, and I've annotated this figure of one of our antennas as if it were a single telescope. The light is collected by the optics of the telescope, which focuses the light on a focal plane and forms an image. That image is then recorded, usually by electronics these days, for later analysis. The characteristic of a telescope that's important for astronomers, one of the characteristics, is its angular resolution, how fine a detail you can see on objects in the sky. And with a single telescope like this, the angular resolution depends on the diameter and the wavelength, or the frequency at which you're observing. And the combination of those two parameters for a telescope the size of one of the SMA antennas gives a resolution of about 36 arc seconds. That's about 1/2 of an arc minute. The moon, for scale, or the sun for that matter, those are about 30 arc minutes, about 1/2 a degree. So this 30 arc seconds is about 1/60th of the size of the moon. It is also about the same resolution as our eyes, as the human eye can see. So that is, as I said, it's about the same resolution as the human eye, but there are many things that we would like to see that are more, that are smaller than that. And so a technique has been developed to combine the signals from arrays of antennas to get higher angular resolution. And as an analogy, I'd like to, so here's a schematic of an array telescope where we take the light that's collected by all of our 8 antennas, we convert it to electronic signals, we transmit it over fiber optics to our central building, where we have a pile of electronics that combine the signals and calculate the image that of the object we're looking at this. How does this work? Let me, by analogy, talk about hearing in animals, humans. We have 2 ears, and when we hear something, we can instinctively tell where the sound of the source is. For instance, if you hear a songbird off to your right, instinctively you'll know it's off to one side of you. And how does that work? The sound from the bird takes more time to reach one ear than it does to the other. And our brain can process that time difference, and through understanding the time difference between the sound arriving at our ears, can then triangulate to determine the direction to the sound. If you imagine you had a chorus of birds all singing different songs, then you could determine the directions to all of those birds and get a mental image of the distribution of the birds. The same thing applies with a telescope array. Here, if I have a simple example where we have two antennas, they're looking at a source, and the light from the source arrives at antenna number 2 before it arrives at antenna number 1 because of the geometry. There's a little extra path in the light path to antenna number 1, and that path depends on the angle between the looking angle of the source. We can compute a time delay from that path. We can measure that time delay, the relative time delay between the light arriving at the two antennas, and we can infer the angle to the source. Again, you can imagine if you had an array of sources, such as would make up an image, you could determine the angle to all that array of sources and then build up information about an image build up information about an image. If we have more than two array antennas, if we have a collection of antennas, then we can treat each pair of antennas as a simple two-element, what we call an interferometer. And this is how the submillimeter array works, combining the signals pairwise between pairs of antennas. This is advantageous because then when we have an array antenna, the angular resolution of the images that we construct from the data we collect depends on the separation of the antennas, not just their size. And for our most compact configuration of all 8 antennas, where they're very close together, they form a circle about 30 meters in diameter, and that has a resolution of about 6 arc seconds, so about 6 times better than an individual antenna. In our very extended configuration, we have a separation of about 500 meters, and we have a resolution about a factor of 10 better, about half an arc second. So we can make very high resolution images with the submillimeter array. We have 8 antennas, but we actually have 24 places we can put these antennas on Mauna Kea. This is a map. All the dots are antenna stations where we can put antennas, and then we have a road network for moving them about. As I said, we have 4 configurations, and these show the configurations which are roughly circular configurations of the antennas, and the four standard configurations we use to accommodate different scientific goals of the scientists who use the submillimeter array. Okay, we are able to reconfigure our array. We move the antennas around from one station to another. Roughly every 6 weeks, we reconfigure our telescope to adapt it to the scientific demand. We have this big yellow machine, the antenna transporter, that picks up the antenna and moves it from one station to another. This video has been sped up by about 4 times, so our technicians are very careful when they're doing this. Of course, it's a very delicate operation with a heavy, expensive piece of equipment. But they can, on a good day, they can relocate up to 3 antennas per day. So generally, reconfiguration takes us a couple of days every 6 weeks. The antennas have advanced instrumentation inside them. Inside each antenna is a receiver, which I've shown in a photo on the left. This is a cryogenic system that holds the active elements, which are superconductor, insulator, superconductor diodes. at very low temperature, liquid helium temperature, about 4 degrees Kelvin. And then there is a large number of support electronics and cabling to support those receivers. There's one of these receivers in each of the antennas that allows, there are, inside each receiver, there are 2 channels at each of 2 wavelengths. So a total of 4 different channels that we can select for different science purposes. The signals are then transmitted over fiber optic cable to our central building. And on the right, I show a picture of some of the signal processing electronics in our central building. This is approximately 1/5 of the amount of electronics in that central building. Electronics these days is, to my mind, not terribly photogenic. It's lots of racks full of cables and boxes that look very similar to normal PC computer boxes, but this is a very powerful signal processing system that takes all the data from our antennas and then records it, processes it, and records it for later analysis. Okay, so now I'll talk a bit about the science we do with the submillimeter array. Submillimeter array is used for high resolution imaging and spectroscopy to advance the understanding of a broad range of astrophysics. This little sampler shows the sort of things we look at with the submillimeter array. Many of the pictures we make actually they're very small scale. We're looking at details, small details in a relatively small field of view. And we always display them at the maximum resolution that we can. So often the images look kind of fuzzy because we've expanded them to the point where we're trying to look at the maximum details we can see. But from left to right, on the left, the one labeled LKCA15, that is a protoplanetary disk around a young star. And the structure of that disk indicates the possible formation of planets around that star. The red one in the center is the shells of molecular material around an evolved star, IRC 10216. Then moving right, there's a G240, which shows the magnetic field in a outflow around a young star. On the right-hand side, the green spectrum, which I'll come back to, is the spectrum of ionized carbon in a very distant galaxy. Along the bottom, the red and blue panels show molecular outflows around young stars and the different shapes those molecular outflows take. And finally, on the lower right-hand side is the lensed image of a very distant galaxy in red, the distant galaxy detected with the submillimeter array, and the foreground lensing galaxy in grayscale is an optical image of the foreground lensing galaxy. And I'll talk a little bit about lensing in a moment. We observe objects from the nearby solar system objects out to the very most distant objects in the universe. This object, this picture, is a picture of an asteroid that came close to the Earth, closer than the moon. about a little less than 10 years ago. And the submillimeter array was able to observe this object. Asteroids, from the point of view of submillimeter astronomy, are warm rocks. And we can determine their temperature by looking at them at different wavelengths to determine their color. We can also determine their brightness simply by measuring the brightness in the image. And from the combination of the temperature and the brightness, one can, and the assumption that this is essentially a warm rock, you can determine the size, the average size of the object. And it was determined that this object is about 300 meters in diameter, which is small for an asteroid, but for something that's coming that close to the Earth is somewhat worrisome. If an asteroid that big were to hit the Earth, it would be quite spectacular. These observations were able to refine the measurement of the size of this object from the initial estimates were about 25% larger, and these measurements refine the size of the object. So that's a very close object. Moving out, another solar system example is looking at methyl cyanide in the atmosphere of Titan. Titan being the moon of Saturn. And this shows the distribution of methyl cyanide in the atmosphere of Titan. The grid shows the outline of the moon, and then the color is false color. Red is most intense and blue is least intense of the molecular methyl cyanide in the atmosphere. And this shows a strong north-south difference, where it's brighter in one hemisphere than the other. The abundance seems to increase with altitude in the atmosphere. And from the motions of the gas, we can determine their stratospheric winds of about 200 to 300 meters per second in Titan. Another planetary example is hydrogen cyanide in Jupiter's atmosphere. About a bit more than 25 years ago, a comet impacted into Jupiter. This is a picture. You can see a picture of the comet. The comet fragmented before it impacted Jupiter. At the time, the impact was just on the backside of Jupiter, so it was not directly visible from the Earth, but the aftermath was visible from Earth. The dark splotches that you see in the image of Jupiter up on the upper left were remnants of the comet impact in Jupiter. That injected some exotic molecules into the atmosphere of Jupiter, including hydrogen cyanide. And the SMA was able to image the distribution of hydrogen cyanide in Jupiter. And what we see here is that the hydrogen cyanide is concentrated in the equatorial regions and absent in the polar regions, indicating there's some downward polar vortice that takes the hydrogen cyanide out of the atmosphere in the polar regions and pushes it deeper into the interior of Jupiter. The SMA is a spectroscopic instrument, and this is a wideband spectrum of a source just to indicate the potential for measurements of astrochemistry through spectroscopy. Each molecule, of which there are a couple of hundred known in the interstellar medium, has a distinct spectral signature. And when we look at a source, we will see bright lines at precise frequencies that correspond to different molecules. And here I show some data from the SMA over a wide spectral range at the 1.3 millimeter wavelength. And it's the same data, but with the spectral scale expanded in the lower panels. And we see in the upper panels several lines from methanol, and then a line from carbon monoxide, very strong emission lines from those molecules. The middle spectrum shows sulfur dioxide and HC3N. Don't remember my chemistry on that one. And then the lower blow up of a more a smaller region shows 3 lines over on the left from methyl formate, and a whole number of lines labeled A from methanol, but this is methanol with a different isotope of carbon, 13 carbon instead of 12 carbon. So we can determine not only the chemical species, but the nuclear isotope that is in the chemical, and we can differentiate between isotopomers of different molecules. As I said, there's a rich astrochemistry in the interstellar medium. This image shows an evolved star. This is a star in the very late stage of evolution. And stars in the late stage of evolution emit periodic, they have stellar winds that push out a large amount of material from the outer atmospheres of the star into the interstellar medium. And these winds can be periodic. They can vary in a regular pattern. This star is actually in a binary system. So as the star rotates around, orbits its companion in the binary system, the stellar wind and the shells of material that are expelled by the star get pushed out, and they get pushed as they move out. They form a spiral pattern, which you can see in this image. There is a helpful lines to guide your eye, and the spiral pattern is caused by the combination of the mass loss from the aged star and the binary motion of the star around its companion. Okay. Moving to continuum measurements, we have measured a galactic X-ray binary source. This is a source where you have a black hole that in the upper left-hand corner is an artist's drawing of it. You have a black hole which is sucking material from a normal star that orbits it. And the black hole is much heavier, but of course much smaller than the normal star. And as the material is drawn from the normal star onto the black hole, it heats up to very high temperatures and releases bright radiation. The flow of material from the normal star onto the black hole is lumpy, and this causes flares in the radiation from this system. And the image that is brightening and darkening was one of these flares that was observed with the SMA, again at 1.3 millimeter wavelength. in about half an hour, this system increased its brightness by a factor of 100 and then faded back. So this is quite spectacular increase in the brightness in a very short time. So we do time-resolved astronomy as well as looking at objects that are static. I'm going to skip over a very important part of field because it's a little hard to visualize, and that is measurements of molecular clouds in our galaxy. Molecular clouds are the locations where stars form. Molecular clouds of molecular hydrogen are drawn together by self-gravity, cool off and contract and form new stars. The stars then evolve and disrupt the clouds, and eventually the clouds recollapse and the cycle continues. The submillimeter array is an instrument for making detailed images of relatively small fields of view, so it's not a very good instrument for making a picture of the entire distribution of gas in our galaxy. But if we look at external galaxies, the submillimeter array is well matched to measuring the distribution of molecular gas and star formation in external galaxies. And this is a picture of a almost edge-on spiral galaxy, optical image on the left, and an image of molecular gas on the right. And the image is color-coded. The contour lines are the intensity of the emission, which is a measure of the amount of the gas that's there. The colors show the relative velocity of the gas, where the blue material is moving towards us, and the red and pink material is moving away from us. So we can determine that this galaxy is rotating in the sense that the top of it in this picture is moving towards us, and the bottom of it is moving away from us. The entire disk is rotating, and there's this ring of molecular gas surrounding the nucleus of the galaxy, where star formation is occurring. Another galaxy, a very famous galaxy, the Whirlpool galaxy, is a almost face-on spiral. It has been well studied at many wavelengths, and this shows the molecular gas in the carbon monoxide, which is a tracer of molecular hydrogen. In this galaxy, the contours and color scale is the intensity of molecular gas in the galaxy. This galaxy has a very prominent spiral pattern that is accentuated by gravitational interactions with its companion, which is on the lower left-hand corner. That gravitational tidal interaction amplifies the spiral pattern in this galaxy. Another thing to notice in this galaxy is along the spiral arms, there are a number of dark clouds formed by interstellar dust. And interstellar dust is small silicaceous or carbonaceous compound particles analogous to smoke in a daily analogy. And those particles of dust obscure the stars. They are also tracers of interstellar gas clouds where star formation occurs. And we see that the molecular gas is preferentially aligned along the spiral arms and also along the dark dust lanes in the spiral arms. You'll also notice there's a number of bright blue stars along those spiral arms, those are new, hot, massive stars that have recently formed along the spiral arms. This is a detail at higher resolution of a spiral arm in the Whirlpool galaxy, where we can actually start to resolve individual molecular cloud associations along the spiral arms. Okay. I said I'd talk a little about gravitational lenses. A gravitational lens is formed when there is a massive object, such as a cluster of galaxies, between us and a very distant object, such as a quasar or a very distant galaxy. The gravity of the intervening object bends the light so that from our point of view, we will see two or more images of the background object on either side of the lens of the gravitational lens. And this is a diagram of the geometry. You can, it's a little early in the morning for this experiment, but later in the evening, you can play with making a gravitational lens if you have a light source, such as a candle, and a rather lumpy piece of a glass, such as the base of a wine glass. This has somewhat the same properties as a gravitational lens, where you can see the candle is refracted into multiple images, or perhaps even a ring, by the shape of the glass in the wine glass. This is not obviously a lens that you would use for fine photography, but it is still a lens of a type, and it is somewhat analogous to a gravitational lens. And what we see here is an image. The red image was taken with the submillimeter array of a very distant background object. And the blue image is the foreground lens object taken in the visible with the very large telescope in Chile. And the foreground object is not visible in the submillimeter, and the background object is not visible at optical wavelengths. So we can look at different types of galaxies in the early universe by taking advantage of these gravitational lenses. And this is a paper that appeared in Nature a little while ago, highlighting a very distant object. This is a lens galaxy in the very early universe. And it is, we can measure the amount of molecular gas, carbon monoxide, as a tracer for molecular hydrogen, but also ionized carbon in the upper left-hand corner. That was this was done in conjunction with another telescope, but the SMA contribution was measurement of ionized carbon. And that tells us about the conditions in the interstellar medium in this galaxy. This galaxy exists only 1 billion years after the Big Bang, so about almost 13 billion years ago, well before the creation of the Earth, before the Earth and the solar system were created. And it already, at this very early time in the universe, it has very vigorous star formation and copious amounts of carbon, oxygen, and other metals, other heavy elements beyond hydrogen and helium. And so it shows that creation of heavy elements occurred very, very early in the universe. I should also point out that normally it's very difficult to observe ionized carbon. It's the free wavelength of ionized carbon. This ionized carbon line is 158 micrometers, which is in a part of the atmospheric spectrum that is completely opaque and very difficult, impossible to observe from the ground. But because of the very great distance, the very early time of this galaxy, the wavelength is shifted into the submillimeter wavelengths where we can observe with the SMA. Okay, the last thing I'd like to talk about is the Event Horizon Telescope, and I'll put in an advertisement for my colleague Shep Dolman, who will be giving another talk in this series in a few months, completely devoted to the Event Horizon Telescope. But I'll give you a preview right now. The submillimeter array, as I said at the beginning, is an array telescope made of 8 individual antennas that work together as one telescope. And the reason we do that is that we can spread the antennas apart and obtain high angular resolution by combining the signals from antennas that are spread apart by a distance. You can extend that concept to its practical limit by spreading out antennas across the entire Earth. And Shep Dolman and his colleagues have been at this for quite a number of years. I've known Shep for almost 25 years now, and he's been doggedly pursuing this goal over those years. And he has put together a network of telescopes ranging from Spain to Hawaii and from Arizona to the South Pole to observe very bright objects, in particular this supermassive black holes at the center of galaxies. And I'm sure most of you have seen this image of the black hole in the center of the galaxy M87, which was released in, the observations were made in 2017, and the image was released 2 years later in 2019. What we see here, the bright emission, is from the high temperature accretion disk that surrounds the black hole, and then the dark spot in the middle is the actual black hole casting its shadow on the accretion disk. Shep will explain more, but because of the bending of light by gravity, you can actually see the accretion disk all the way around the backside of the black hole, and the black hole appears as a dark spot in front of this accretion disk. This is very high resolution. As I said earlier, the submillimeter array at its maximum resolution has a resolution of about 1/2 of an arc second. This technique allows a resolution of tens of micro arc seconds. So almost 100,000 times more resolution than the SMA, which is simply a reflection of the increased distance between the antennas in the Event Horizon Telescope. The SMA, along with our neighboring telescope, the James Clerk Maxwell Telescope, which is the building just to the left of the SMA hangar there, both on Hawaii, have been key stations in the Event Horizon Telescope for many years. This set of images shows how adding data from different pairs of antennas improves the image that one can get of M87. In the left-hand image, we just have data from Arizona and Mexico, and we see a round distribution. If you add in data from the telescope in Chile, you start to see some structure, and add in Hawaii, a ring becomes more apparent. But when you add Hawaii and Spain with the others, then you have the resolution and imaging capability necessary to see the ring around the black hole. This ring around the black hole is not static. There have been experiments of this technique, at least for the last 10 years. There was early data in 2009 between Hawaii and Arizona and California. And subsequent to the image that was released in 2019 with the full Event Horizon Telescope Array, some of the members of that collaboration went back to some of the archival data, the earlier observations. And even though those earlier observations were not sufficient to form an image, they were sufficient that when constrained by a model based on the full image made in 2017, to show, the earlier data showed that the distribution of light around the black hole had changed over the years. And you can see the distribution of light where the bright spot is moving around the center black hole over the years. And the SMA and JCMT on Mauna Kea have been key elements in these efforts over the past 10 and more years. As I said, Shep Dolman will be discussing this at a talk in May. So I've given you a little overview of what the SMA is, the submillimeter array is, and what we do with it. I'll leave you with this photo of the SMA and some of the other telescopes on Mauna Kea, and I'd be happy to answer any questions. I believe Stephen is going to be moderating the questions, so I'll turn it back over to him.
Okay, thank you for all the information, Dr. Radford. We do have a few questions. From Jeff, he asked 2 questions, and I'll just give them to you both. First one's pretty short, but when did the SMA see first light? And do you make observations during the daytime, or you strictly have to do dark outside to do all of your observing?
So the SMA, the dedication was in 2003. First engineering observations on Hawaii with telescopes on Mauna Kea were made in the late 1990s, 1998 or 99. This is before I joined the project, and design work began in the early 1990s for the array. We preferentially observe at night. It's not really a question of daylight so much as atmospheric stability. We rely on the atmosphere to be stable, and weather conditions are generally better at night than they are during the day. But we do observe during the daytime on occasion when the weather is good, or quite often for engineering or technical tests we can carry out during the daytime.
Okay, thank you. Another question from Anya. Do workers moving the antennas and doing the maintenance ever need oxygen with the high altitude you have there? Mauna Kea is high enough that altitude sickness and hypoxia are a concern. We are, of course, very concerned for the health and safety of observatory staff. It is not so high that you cannot work without oxygen. Some workers do use supplemental oxygen. Our control room is, we have a small control room in the building, and that has enriched oxygen by a few percent, which has the effect of lowering the physiological altitude. But not all
workers choose to use oxygen. It's a bit of a matter of personal preference.
Okay, from Jeff, he asked, what causes the negative flux density measurements of the lens galaxies?
Negative flux density measurements. I'm not quite sure I understand that question, but I'll give it a try. If we look at an object through a gravitational lens, the lens is along the same line of sight as the object we're interested, but that does not mean that the two objects are radiating at the same wavelengths. The background object, which we may be looking at the submillimeter wavelengths, may just simply not be bright at optical wavelengths, and the more nearby lens may be bright in the optical and not bright in the submillimeter, simply because of the intrinsic properties of the galaxy. Then the lens bends the light from the background object, so we see images of the background object on either side of the lens. And that causes this ring type appearance of the lens. I hope that answers it.
Okay, you can ask it again if didn't quite get it. Another one from Doug is, did you have a chance to image Oumuamua? If so, did you come to any conclusions? Probably related to Dr. Loeb's last lecture, our first lecture we had in our series.
Yes, I have the pleasure of trying to follow up Avi Loeb, which is a hard act to follow. No, we did not have the opportunity to observe that object, and I do not have any personal opinion about the nature of that object. It's really outside my field to speculate on.
Okay, good enough. From John is, for M51, is it true that the two galaxies are not interacting?
I believe they are interacting. I would have to double check that, but my memory is that the companion galaxy is interacting with the main galaxy, and eventually they will merge together. I would have to double check a reference, but that's my memory of their interaction.
Okay, another question from Sue is, she only sees 7 telescopes in the view that you have posted right now. Is the 8th one hiding someplace, or?
I congratulate her on her perceptivity. We have 8 telescopes. We conduct maintenance on roughly 4 telescopes a year, and each maintenance period takes about a month. We take one of the antennas for maintenance into the hangar, perform preventive and corrective maintenance. So when you do the arithmetic, doing 4 antennas a year for a month, we typically have 7 2/3 of an antenna average deployed. So yes, in this picture, when this picture was taken, one of the antennas must have been in the hangar.
Okay, good. Now we know the answer.
Yeah.
Are operators on, this is from Jeff, are there operators on the mountain, or are the telescopes operated from a lower altitude? And how many operators are there perhaps when the array is operated robotically?
So I'll answer in reverse order. When the array is operated, we usually have only one telescope operator. who may be in Hilo, Hawaii at our office. We have an office building on the campus of the university. Maybe in Cambridge, Massachusetts at the Center for Astrophysics. Maybe in Taipei at the EHT in Taipei. Usually only one person is operating the telescope. Especially this past year, we were moving towards primarily remote observation anyway, and this past year, circumstances have accelerated that trend. Almost all of our observations are made remotely from one of those three places, Hilo, Cambridge, or Taipei. During the daytime, however, we do have technicians during the week and operations staff on the weekends. During the daytime, during the week, the technicians are carrying out technical work, maintenance, upgrades, this sort of thing, or in fact, moving the antennas from one place to another. On the weekends, we carry out engineering tests and other test observations. When we observe during the day, we like to have operators at the telescope in case something goes wrong, they can intervene during the day, which is more difficult when they're remote. The total staff here in Hawaii for the submillimeter array is about 20 to 22 dozen people, mostly Smithsonian, with a few people from Asia in the group as well.
Okay, it looks like that's all the questions at this time. I'm sure I like the wine glass analogy. I'm sure everybody should remember to drink the wine before they hold it up to the candle and do that. So that's all we have for well, no, we just had a question. How does using only 7 antennas affect the geometry of the interferometry?
Oh, that's a good question. As I said at the beginning, we collect the data based on pairs of antennas, and the number of pairs goes up quite rapidly with the number of antennas. So unfortunately, when we only have 7 antennas, we have less data, less imaging data than we would with 8 antennas. It's not simply the additional sensitivity, but the imaging data we lose, which is unfortunate. It means that our images take longer to acquire, and they're not quite as good as they would be if we have 8 antennas. On the other hand, we do have the practical constraint that we do need to maintain and repair antennas as time goes on, not just the antennas, but the instrumentation in them as well. And it's not really a choice. You know, if you have 7 antennas, we observe with them. You know, the alternative of not observing at all is not very palatable, and we do need to maintain our antennas. An ideal solution, of course, would be to get yet another antenna, and then we could have 8 in the field and 1 in the hangar instead of 7 in the field and 1 in the hangar. You can always use more antennas. You know, there's other sayings about never having too few antennas that's analogous. But thanks for the question.
Okay, I think that gets it. We'll bring Amy back in here to wrap things up. And I appreciate everything I've learned today. So Amy.
Well, thank you, Stephen, for conducting the question, and thank you all for asking questions.
Well, and yeah, thank you so much, Simon. I mean, it's always interesting to hear from you. And you never have to worry. I heard you say you had to follow Avi and that's difficult. And he's interesting in his own way. And what you do is so interesting on these other levels and in a different area of science. So you don't have to worry about who you're following. You know, Shep has it the hardest because he has to close out the series this year. So he has to make a huge bang. Thank you so much to everyone who joined us today. And if you were here with us today and needed captions, please go ahead and email me at oliver@si.edu, and I will make sure you get a copy of this video with captions right in the video. I know that was a struggle for some people today. We're not quite sure why captions didn't turn on, and I give you my deepest apologies for that, but we will make sure that you get either a DVD or a link to a video that you can download so that you can watch with captions. And thank you again for joining us. And Simon, thank you again so much for being here. Stephen, thank you so much for all your hard work. And we'll see you again in 2 weeks when we welcome Dr. Kimberly Arcand, who is a visualization specialist and sonification specialist at the Chandra X-ray mission. See you again soon. Bye.
Bye-bye.